I woke up at 9 a.m. Yes. Really keys to the things that trust that I put into. So, okay. And yeah. But speakers. Yeah, that's right.
Okay, let's get started for this week. Is there like some event or something going on? I feel like we have far fewer people than usual.
It's just I
do wish that that my classes are the type where I could just do it on in Henley Plaza or near the Cathedral lawn or something. That would be nice, wouldn't it? Like if they gave me a big chalkboard or something that I could put there, that would work. I like having the slides, but I can lecture from on a chalkboard, especially if it's nice out. Throw a few frisbees around. Okay, well, anyway, so I guess we are not lucky enough to do that, but let's hope that we make up for it with some interesting physics or from computing. Okay, so there's the outline, probably a bit ambitious. So we'll see how far we get into this. I want to try and finish up talking about multiple qubits. We introduced the single qubit quantum gates last time. I'll quickly review that. Go into the 2-qubit discussion. We just started it at the end of last class. Not today, but hopefully by next class, we'll get to the no cloning theorem and maybe a little bit about how to convert any classical gate to a quantum gate. Okay. And yeah, if I have time, we'll cover some universal quantum gates. Okay, so quickly to review from last time. If we have a 2-qubit state and we want to apply a single gate to the first qubit and leave the second qubit alone, that is, if 0, 0 is our starting state, we want to put a Hadamard on the left qubit and leave the right qubit alone. How do we do this? We saw the answer last time, and the answer is to take a tensor product between the Hadamard gate and the identity gate. Okay, and we saw last time how to do that. Or how that would work. So H will purely act on the left qubit here, and I will purely act on the right qubit here. So H acting on the left qubit gives me 0 plus 1, okay? And I acting on the right qubit leaves me in the 0. So that's 0 tensor 0 plus 1 tensor 0, and of course the 1 over root 2 outside. And that can be rewritten in our compact notation as 1 over root 2. 0, 0 plus 1, 0. And I also pointed out that this can be viewed as the column vector, because remember the column vector is labeled by the coefficient for 0, 0, 0, 1, 1, 0, and 1, 1. So that is the column vector that corresponds to this state. And we use the following convention for writing a quantum circuit for gates, which is that the rightmost qubit is the top row of the circuit, and then the qubit to the left of it will be the next row down, and the qubit to the left of that will be the next row down, and so on and so forth. And that's the standard in all of the 3 things that we are using in this course. But there might be other places where that's slightly different. Okay, and so, for example, the quantum gate that I just wrote down, which is identity acting on the right qubit, well, that appears on the top row, because the top row is the rightmost qubit, and then Hadamard acting on the left qubit. So that's the equivalent quantum circuit representation. And since identity does nothing to the qubit, we often will leave it out and just represent that by a wire. Okay. So in the last class, I promised that we'll go through the full matrix representation. I want to do this carefully because This procedure is what you follow for every quantum gate. When you want to figure out what the matrix representation for a quantum gate is, what you do is you act with that quantum gate, whatever that quantum gate might be, on these four states, 0, 0, 0, 1, 1, 0, and 1, 1. So let me go through this example and we'll do, and we'll make sure we understand how to do this because that helps us to know what the matrix representation is for any quantum gate. If you specify, essentially what I'm saying is if you specify what a gate does to those four basis states, 0, 0, 0, 1, 1, 0, 1, 1, you have specified the gate fully. So that's what we want to make sure we know how to do. And it's pretty simple to understand because you've seen examples with the 1 qubit gates. So hopefully this will become pretty clear to you after we do one or two. Look at you chunk. We want, hey, I already showed you how to do H tensor I acting on the 0, 0 state. We already covered that in the last lecture. So I'll just do now say acting on the state 0, 1. Okay. So this state is simply H acting on the 0 qubit and identity acting on the 1 qubit. So that is going to give me 1 over root 2 times 0 tensor 1 plus 1 tensor 1. Everybody see that? Why that is? So H acting on the 0 state produces the state 0 plus 1 over root 2. And therefore, this is the equivalent representation using the tensor products. Okay. An identity acting on 1 does nothing to the 1 state. So you have to think of H acting on both of these, right? On the first qubit and I acting on the second. Or left and right. So this can be written in our compact notation as the 0, 1 plus 1, 1 state. Okay. And in the linear algebra notation, it is 1 over root 2. Remember, the first element is the 0, 0 state on the output, which is 0 here. The second is the 0, 1 state, which is 1. The third is the 1, 0 state, which is 0. And the fourth is the 1, 1 state, which is 1. Okay? Everyone follow this? And H tensor I on the now on the 1 tensor 0 state. Again, we will write down 1 over root 2. Now H acting on the 1 state produces 0 minus 1 over root 2. So this is 0 tensor with 0. That part is easy enough. And then the minus 1, I have to put here, tensor with 0. Okay. So again, in matrix form or column vector form, this is 0, 0 has a 1. 0, 1 has a 0 in front of it because there's no 0, 1 term. And then 1, 0 has a 1, and then 1, 1 has a 0. And of course, the compact notation for this is just 1 over root 2, 0, 0 minus 1. Okay. Any questions so far? And the last term we need to know is how HI, this gate, acts on the 1, 1 term. It's now 1 over root 2. And now H acting on 1 will give me what? Yes? Yes, the minus state, which is in terms of zeros and ones.
One of its derivative two times its zero state minus the state.
Exactly. And so what do I write here? So is it zero state minus one state? That's the action on the left qubit. And then what do I fill in here? For the right side, the right qubit. Yes?
Just tensor of one.
Yes, exactly. Because identity doesn't change, what happens to the right qubit? So this is again in our compact notation, just 0, 1 minus 1, 1. And in the column vector is 1 over root 2. It is 0, right? Because there's a 0, 0 is the top term. And then the next term is? Anyone? What's the next term down here? Is it a 0 or a 1? What do you think? Anybody? Yes?
The one.
It's a 1. Okay. Everybody understand this? Why there's a 1 there? Then what's the next term? Somebody else. Start calling on people. Edit. You don't know? Why not? What's confusing you?
I don't know like how to convert those tensor products to the matrix.
Okay, all right, very good. So the way you should think about that is very similar to how we remember. Okay, let's go back to the original ket 0 term. Okay. Ket 0 was represented as a column vector as what? Do you remember that?
0.
Very good. Exactly. And ket 1?
The 0, 1.
Very good. Okay. So when we write 0, 0, which is 0 tensor 0, right? That's okay with you? What we're doing is we're taking the tensor product of these two or the Kronecker product of these two column vectors. So let's write that down. That's 1, 0 tensor with 1, 0. Okay. And to find that, I have to write down 1 times 1, 0 and 0 times 1, 0 in here. Can you see? Sorry, it's way down there. So that is just the column vector 1, 0, 0, 0. So the state 0, 0 is represented by a 1 on the top element and zeros on the next. If you do 0, 1, it will be 0, 1, 0, 0. 1, 0 will be the next element down, and 1, 1 will be the last element. Does that make sense?
Yeah.
Okay, very good. So that's how we came to the basis states. So you have to think about like in the 1 qubit basis, 0 was the column vector 1, 0, and 1 was the column vector 0, 1. Now we have 2 qubits, there are 4 basis states, 0, 0, 0, 1, 1, 0, 1, 1. So we need 4 of a column vector with 4 elements in it, and we have just concluded that 0, 0 is say 1, 0, 0, 0, 1 is 0, 1, 0, 0, etc., etc. Does that help?
Yeah.
So you can think of like, this one represents the 0, 0 state. Then the next one represents the 0, 1 state, and so on and so forth. Okay. And the most general state, so if I ask you now, I wanted you to write down, say C1, 0, 0 plus C2, 0, 1 plus C3, 1, 0 plus C4, 1, 1. It's a column vector. What would you write here? That's the most general for 2 qubit state I can write down, right? Because it's complex number times 0, 0 state plus 0, 1 plus 1, 0 plus 1, 1. So how would I write that as a complex, as a column vector or linear algebra notation?
Let's do the 1, 0, 0, 0.
Would it just be that?
Yeah, I'm sorry, I'm not like 100% sure.
Okay, so let's go through that as well. So it's C1 times the column vector 1, 0, 0, correct?
Oh, okay. So
Plus C2 times the column vector 0, 1, 0, 0 plus C3 plus C4. So what do you think it is now?
C1, C2, C3, C4.
Exactly, that's it. It's linear algebra. Yeah, everything is linear. So whenever you're in doubt, just think about how you would go about doing it in a linear fashion. Yeah, I'm glad we had this because it seems like I may have left some of you behind on the linear algebra stuff for the 2-qubit stuff. And yeah, I know the 2-qubit stuff is a little bit more advanced, so it takes a little longer to process. You got to go back and maybe review it, maybe look at the video again. From you have the video, you have the slides, so just make sure you're going back and looking at that if you're not sure of what's going. Okay. Okay. So to finish our story here, okay, I'm going to erase this aside at least. Confusing? So to finish our story now, Erin, can you tell me what will this state be?
0, 1,
Mm-hmm.
1, 0, 1, 0, 1.
0, 1, 0, 1. There you go. Oh, one small mistake.
0, -1?
Yes.
Okay.
Very good. Yeah. Okay. Did we mess up anything here? Oh, we missed out a -1. Nobody spotted that. Why did nobody tell me? I know we all would like to be outside, but right now we have to be looking like this again. Okay. Yeah, those are the things which will usually get you, especially when you do long calculations. If you make a mistake on a minus sign, it'll screw you up. So. Okay, so now that so far what I've done is, let's also talk about this because this is important too. So I've told you how HI acts on the 0, 1 state, on the 1, 0 state and the 1, 1 state. I also wrote down, sorry, if I write here, can you see? No, right? Probably not. Those of you over there can't see. All right, let me just give you the result from the notes last time, which was which I just wrote down, but I erased. So let me write that again. Yeah, which is H tensor I acting on the 0 state, 0, 0 state, which we did, which I just showed you on the is 1 over root 2, 1, 0, 1, 0. Okay. So we have now the action. So let's make sure that everybody's following this part. So notice we have the action of the gate HI on 0, 0, which gives me this column vector. Okay. Then acting on the 0, 1 state gives me this column vector. And then acting on the 1, 0 state gives me this column vector. Acting on the 1, 1 state gives me this column vector. And to write the matrix representation, the linear algebra representation for this gate, HI, I simply take each of these columns in order and stack them into a matrix. Meaning, I put this as the first column because it's the 0, 0 column. Then this is the 0, 1, so that's the second column in the matrix. This is the third column in the matrix, 1, 0, minus 1, 0. And this is the fourth column in the matrix. Okay. Does that make sense to everyone? So the matrix representation is simply this column 1, 0, 1, 0, that one 0, 1, 0, 1, then 1, 0, minus 1, 0, and then 0, 1, 0, minus 1. Okay. All one after the other in a matrix form, which I'll just show you on the slide in a minute. But it's basically taken from each of these columns, these column vectors. That's how we get the various columns of the matrix that I'm about to show you. With that. So, sorry, ignore this for a minute. That's just the Kronecker product, but that's exactly the rows, the columns we just wrote down. 1 0 1 0 0 1 0 1 1 0 minus 1 0 0 1 0 minus 1. That's exactly what we had on the board behind. But if you don't trust me, you can go back and verify yourself as well that this is indeed the matrix that we just showed. Each of the columns. Is that clear to everyone? So this is the way we can get the representation without worrying about Kronecker product for a minute. This is how we can get the representation for any gate. Any gate, if I tell you how it acts on 0 0 0 1 1 0 1 1, and I know what it produces, then I just stack those as the different columns of the matrix, and that's the matrix representation of that gate. So I just need to know how the gate acts on 0 0 0 1 1 0 1. Then that gives me immediately the matrix representation. Is that clear to everyone? This central idea, how to go from knowing what a gate does to its matrix representation. Is that clear to everyone? It's kind of like a truth table, if you want to think about it that way. When we did classical logic, we had a truth table which told us, given some input 0 0 0, what is the output? Okay. Well, the output here is not just a single bit, but it's a row, right? Or it's a column of numbers, complex numbers in general. So that's what we need to know to specify what happens when the gate acts on the input string. Okay, now I can introduce the tensor product notation. So we just wrote down H tensor I. We know that H is a 1 qubit gate, which has this matrix representation, which we've already seen many times in previous examples. And this is the identity gate in the 1 qubit case, which is 2-dimensional because the qubit is 2-dimensional. So we can now take the tensor product or Kronecker product of a matrix times a matrix. Okay, how do we do that? Well, exactly the same way we just took the tensor product of a column vector times a column vector that I showed you for, we were reviewing what we had done already. So I'll just do it again now, but with matrices. Okay. Exactly same idea as this over here, but with matrices. H, the gate H is 1 over root 2, 1, 1, 1, minus 1. Okay. And the identity gate is, of course, just 1, 0, 0, 1. This is the matrix representation of those gates in the single qubit space. So we want to take H tensor product I or H Kronecker. I take the Kronecker product of the two matrices. What do I mean by that? Well, it's exactly the same idea as this Kronecker product here. I take this matrix and I multiply it into each element of the other matrix. Okay. So to do that in this case, I'll leave that box over there because the analogy to the column vectors will become clear. So it is 1 over root 2. I take the 1 and I multiply it by this entire matrix, 1, 0, 0, 1. Take the 1 over here, multiply it by this matrix. Take the 1 here, multiply this matrix. And the minus 1 here, multiply it by. So that is the Kronecker product. Okay? And that is just, you can see, will be 1, 0, 1, 0. That's this column over here, right? And that, or I can just write it as a block matrix. Probably that's the easiest way to immediately write it down. Okay. Does everybody see how we went to this step? The last step over here. Everybody okay with that? Let me know. Okay. That's how. So what I'm showing you is different ways to get the matrix representation. The first way is by acting on each of the states 0, 0, 0, 1, 1, 0, 1, 1. The second is by taking the tensor product, Kronecker product directly, okay? Because you know the matrix representation. Is that clear? Help me. Yes. That's exactly. You see, if you write it as like a block here, there's 1001, 1001, 1001, which makes sense. It's 1 in the Hadamard, the 1 in the Hadamard multiplying the identity matrix each. And then the last one is just the -1 multiplying the identity. That's this block over here. Okay, and of course, you can do it with Python or Mathematica or any other software package that you like. And it's just one line of code, basically. Because I already in the previous lectures and stuff, we went through and defined all these gates. So it's just NP Kronecker product of H, comma identity, and you get exactly the number that we just got. Okay. Of course, it's not as nice as having Mathematica sometimes, because Mathematica will preserve 1 over root 2 and not try to convert it to a number. So that's the nice thing with Mathematica, is it makes it look prettier. Yeah, when you get, but the final answer, if you work with this gate, will be the same, in those cases. Okay, any questions before I move on to the next topic? All right. So I'm just recalling to you from an earlier lecture that we had a state like this. If you remember, we had a state like that. And we calculated what is the probability to measure 0 on the left qubit. The way we did that was we looked in the superposition, which states will give me a 0 on the left qubit. There are only 2 states, the 0, 0 and the 0, 1 state, because they have a 0 on the left qubit. And that told me the probability, which is just 1 over root 2 whole squared plus 1 over 2 the whole squared, which was 3/4, which is what we got here. Okay. And we can then calculate what happens after it collapses. When it collapses, it basically will collapse into these 2 states, 0, 0 and 0, 1. But then we have to renormalize, which we renormalize by dividing by this square root of this probability. Okay, square root of 3 over 4. And that gives us this formula over here for the collapsed wave function. Okay, so we have talked about this using the Ket algebra notation, but you could imagine if I ask you to now calculate what happens. What if I ask you the probability to measure the plus state on the left hand? If I gave you this general state. Or what if I ask you plus on the left qubit and minus on the right qubit? We can ask that, right? Because we can measure in different bases, as you know, from your single qubit. When we talked about the block sphere and measurements in different bases there, and we saw all the cool things we could do with them, right? We built quantum bond detectors, for example. Okay. Or we showed how a universal Turing machine cannot simulate the action of some of the basic 1 qubit quantum gates, like Hadamard, for example. Okay. So how do I go about doing that here? Well, of course, the one answer is I just calculate. I take the Ket algebra and I figure out, I rewrite each of these zeros and ones in terms of plus and minus, and then I calculate what happens. And that is valid, but it is going to be very tedious. Okay. But the better way, as we introduce now, is through something I call a projection gate. This is not in your textbook, but I think it's a very useful concept and an idea. So I'll try to introduce it slowly, and we can always come back to it. It's not, So what we want to do, right, is we want to write a measurement of the qubit in a Ket algebra form in such a way that we want to construct what I call a gate. Because gates, remember, have to be unitary, but when we do a measurement, it's a non-unitary thing because we are projecting into one state or the other. So this gate, it projects the left qubit to 0, but does nothing to the second qubit. So it's very similar to that example I just showed you, where it was Hadamard tensor with identity, right? Hadamard was acting on the left qubit and identity was acting on the right qubit, which means it did nothing to the second qubit, right? And the first qubit, though, now instead of being a Hadamard, I want to project it onto the state 0. What would be the operator or the gate that would do that? Any ideas? Can I write it in Ket algebra form or some other form that we have introduced earlier? Yes.
Maybe the polymatrix matrix X tensor identity.
X tensor identity.
Is
But X is a gate, is a unitary gate, which means that it will take 0 to 1 and 1 to 0. It will not make. So suppose the first qubit was in the state 1, then this gate should give us a 0 result, right? It should tell us that the total answer is 0 probability, because it has no probability to be in the 0 state, basically. It should collapse the state to like nothing, basically, if that makes sense. Because we want to project the state onto the 0 state. Is there an operation we learned earlier that could do that? That could take a projection measurement or a overlap of the function or the wave function or of the state with one state or any state that I want. Yes. Inner product? Inner product. Getting closer. Yes. That's the product. We're just going to go through all of them. Tensor product, as we saw, was with the 2 qubits, for example. Okay. Yeah, there's one other product we introduced. So hopefully by another. Yes.
The outer product.
Outer product. Exactly. But outer product of what?
The 2 qubits, the 0 state, one you're projecting on, and the leftmost qubit.
So the 0 state for the left qubit, I want to construct an outer product that satisfies. So what is an outer product usually taken between? When we take outer products, what usually are we taking outer products of? What vectors? Yeah.
Ket times bra.
Yeah, very good. Ket times a bra. Exactly. Very good. So what ket and what bra do I have to use? Yeah. I want to project it onto the state 0. You're close, right? You almost have the answer. So which ket and which bra will take me to the state 0? For the left qubit. Okay, let's go back and review outer products and projection operators. Okay. So if I have a state psi and I write it as A times 0 plus B times 1, right? That is our qubit state, correct? And we can write this qubit state as, say, the column vector AB, correct? Everybody agree with this? Now, when I want to find the projection or the amplitude of psi onto the 0 state, what do I do? I mean, yes, of course, it's the norm squared of this, but if I were to give you this state and or this column vector and I wanted to find the fact that this is A, how do I isolate this A? What do I multiply that with? Yes?
Bra 0.
Exactly. Bra 0 ket psi. When I do bra 0 ket psi, which in linear algebra notation is simply 1, 0, the row vector times AB, I get the number A. Right? Everybody agree with this? This is just review of inner product, isn't it? So this number psi 0 over here is the number A. And psi 1 clearly will be the number B. So I substitute back for A and B in here. What do I get? I get psi equals 0 psi times ket 0 plus 1 psi ket 1. So what it's saying is the component of psi along 0, that's an inner product, times the state 0, plus component of psi along the state 1 times the state 1 is the total state. Okay. And what you can do is pull, because this is just a number, I can pull it over to this side and rewrite this as psi equals ket 0 times its component plus this times its component psi. Okay, nothing but just taking this over to this side, I just rewritten the equation. No change has happened. Now I identify this thing here, this function, if you like, it's always hungry for a psi, something on the right hand side. When it finds that thing, it's basically it takes an inner product with that thing and spits out a component along the 0 state. Okay, times the column vector 0, of course. But other than that, it's just exactly the same thing. Okay, so we identify this over here as a projector operator, or projection of, this is, we talked about this, this is the projection of psi onto Z. This thing over here. And this is called the outer product, as you know. Okay. And we can write it using, standard notation like this. And this is a matrix, right? Because this is the column vector 0, this is the row vector 1, 0, and this is now a matrix. Because again, I take 1, 0, and 0, 0. Is that clear to everyone? How we get that? And you can verify for yourself that if I take this 1, 0, 0, 0 and act on the state AB, so that means I do now matrix multiplication. So this operator, which I'm going to call projection operator along 0. Okay. So projection operator along 0, maybe I should say P onto ket 0, okay, is 0 outer product with 0, which is in linear algebra form is 1, 0, 1, 0, which is now a matrix 1, 0, 0, 0. Notice that, and this is not new, we have done other similar outer products in the previous example, but I just wanted to highlight this operator because it's not a unitary operator. You can see that immediately, right? U dagger would be the transpose of this operator, right? Which would be just the same operator itself, right? Because it's just 1, 0, 0, 0. Transpose conjugate of this matrix is just the same as itself. But if I take the multiplication P0 times P dagger or P dagger times P, I don't get a unitary matrix. I don't get an identity matrix. Because that is the condition for unitarity. Remember? If I want a matrix to be unitary, I need P0 dagger times P0 should be identity. And it is not. But this, although this by itself is not an identity matrix, if you now combine it with its other projector operator along the one state, then they turn out to be a matrix. That is just a completeness relationship. Meaning, if I now calculate the same thing over here, I call this projection along one state, which is the 1, 1. Okay. Operator, again, I just do 1, oh, sorry, this is down 0, 1, 0, 1. Okay, again, writing this out, this is 0, 0, 0, 1. Right? You just multiply 0 into this one and 1 into this one, and you get this. Add these two matrices together, P0 and P1. And you get identity matrix. Which is saying that together, these two guys will always give you a result. Because the qubit will always observe to be either in 0 or in 1. Okay? It can't be, in our view of quantum mechanics, it always has to be one of those two states, 0 or 1. When you measure it. Any questions so far? Some of this is review, but some of this is just a new way of looking at the same thing. Okay. So what it is now is this is a gate, not a unitary gate, but I can think of it as a gate because it's a matrix. Okay, it's not a quantum unitary gate, but I can think of it as like some kind of collapse gate or measurement gate. Okay. So now I just told you this is for 1 qubit, right? We've been just doing 1 qubit gate. But now I want to do for a 2 qubit gate, the gate that projects the left qubit onto the 0 state and leaves the right qubit untouched. How would I write this gate? Over here. The gate that will project the left qubit and leave the right qubit untouched. Yes.
We have to do like outer product of 0, 0, 0, 0, 0, 0 plus 0, 1, 0, 1.
0, 0. This is what you're talking about.
No. Exactly.
Okay.
So 0, 0, outer product 0, 0.
0, 0.
Like the two qubits.
0, 0. Outer product 0, 0.
Well, it seems like that's what you want me to say. But that's now.
But outer product, as you can see, still only gives me a 2 qubit, gives me only a 2 by 2 matrix.
So it's like the outer product of it would be.
What is it that will give
4
me?
by 1.
Yeah.
4 by.
So it's got to be a 4 by 1 and a 4 by 1. So that would be, so 1, 0, 0, 0 with 1, 0, 0, 0. Is that what you're trying to say?
I guess reverse order give you a matrix data.
Well, this will give me a matrix.
Okay.
Oh, no, sorry, this one. Yeah, sorry. Yeah. This. This is great. Yeah, okay. So,
But I don't think that's enough.
yeah, very good. Because what this does is, if I calculate this matrix, it's 1, 0, 0, 0, 0, 0, 0, 0 everywhere else. Right? Okay, there's only one. So if I now act on a state, let's take a state, okay? Let's take some state psi acting, let's say A 0, 0 plus B 0, 1 plus C 1, 0 plus D 1, 1. Okay, this is the column vector A, B, C, D. What will this give me? Acting on that. Yes?
Just gave you A 0, 0 or just A.
It just A, right? So if I call this some gate, or G, G acting on psi is just A. And of course, yes, as you said, it collapses the state into the state 0, 0, right? So the state after this is just A 0, 0. Right? But that is not what I want, because I want the state, no matter whether it's, this or the other one, 0, 1, I want that to be projected, but I don't want any of the other things to be touched. So you're very close now, right? Can you see what you might do?
Well, so then you add, well, you put the 1 in the 2 or 1, 1
Yeah.
space.
Yeah, exactly, right there. Very good. That is the matrix. That is correct. But there's a way to write this that makes it a little bit more explicit. Okay, which makes it hopefully more obvious what is going on. Which is, we go back to our friend, the tensor product. That is, we take 0, 0 acting on the left qubit, right? That is the state 0, 0 acting on the left qubit, tensored with identity on the right qubit. And I'll show you that's exactly the same as this one, because we just showed that projection of 0 is just this matrix over here. 1 is equal to 1, 0, 0, 0. That's this state over here. Okay, this operator or gate over here. Now, when I take the Kronecker product with the identity matrix, so I took this matrix over here, and I take the Kronecker product with the identity matrix. I get 1 acting on that, so that gives me the block identity matrix, and everything else is zeros. Just took zeros here. Sort of keeping on writing 0, 0, 0, 0. Okay, it's just zeros everywhere else. And that's exactly what you just came up with by arguing about what we should get. So this is just a mathematical way of writing the operator, the gate, in such a way that by just using the rules of linear algebra, we can get exactly what you just got by thinking about what happens when I project the state, the left state onto the 0 and don't touch the right state. Okay. Is this clear to everyone? Maybe it's a little confusing, I know. And it takes a while. Okay. All of this you probably have to go over a couple of times again on your own as well. And come and talk to me if you still have questions about what's going on. Okay, so that is our way of writing projection gate. And once we write that, so that is just this gate that I wrote on the board, which is 0, 0, tensor product with I. And now we can just write the code for it. So first, we take outer product, just like I did, between 0 and 0, right? That's ket 0, bra 0, that's the outer product. And then I take the Kronecker product, or outer product, tensor product of that 0, 0 times the identity. And that will give me the exact same matrix that we just wrote down on the board. 1, 0, 0, 0, 0, 1, 0, 0, etc., etc. And how do we know that it's working correctly? We take this projector operator, okay, and we multiply it times our ket 0, 0, which is that column vector 1, 0, 0, 0. Okay. So that gives me 1, 0, 0, 0. And then if it's 0, 1, it also gives me 0. So anything that's 0, 0 or 0, 1 will be preserved. Everything else will be destroyed. Right? Because it doesn't touch the second qubit, keeps it. And the first qubit gets projected onto 0. But if the first qubit is 1 and you try to project into 0, you get 0, obviously. So that's all zeros over here. Good. It destroys the state. You can put this into quart as well. So now let's return to the example that I originally told you about. Remember this one? This was the example that we worked it out one by one for the case projecting the 0 on the left qubit, projecting 1 on the left qubit, 0 on the right qubit, 1 on the right qubit. We worked it out by hand, right? By just doing the projection operation. But now that we have constructed a gate, projection gate, I always start to put double quote because it's not a true quantum gate. But in terms of what it does to the states, it gives us what we need. Which is, first I write down the state, which I just wrote down in the slide previously. That is this one. So I construct that state over here. And just to check, print it out. Okay. And now projection operator that I just constructed multiplied by this state, matrix multiplication or using linear algebra rules that we have learned, will give me this state over here. Of course, the state may not be normalized. So to find its normalization, I take its inner product with itself, or the bra times the ket. Okay. So that's the inner product of the bra times the ket. And I have to take the square root of that and multiply it into this state. And I get this new state over here. Okay. So this is saying that it's some number times 0, 0 plus some number times 0, 1. Okay. And then all the others are 0. Okay. And if you now look at our slide earlier, which was that the normalization constant was 2 over root 3 times this, then we get indeed the same numbers over here. So 0.81666 and 0.5777 is just exactly what we had previously. That is, I'm saying all of that is the same as this over here, this statement. So when we use the projector operator, we automatically get the state that's left behind, or the column vector that results, is indeed the state after the collapse. Okay, by just taking that projection operator and acting on the state. So which means now I can generalize. We can construct a projection operator in any basis or on any combination of qubits. So I ask you now, okay, I want to measure the left qubit in the plus state and the right qubit in the minus I state, that is the minus Y state on the block sphere, right? How would I go about constructing the projection gate for this situation? Any thoughts? Yes.
Would be the outer product of plus plus and then tensor product with minus I.
Perfect. Exactly. Everybody follow that? So it's outer product of plus plus. Maybe I should try to write it here. I can. Terrible with this pen. That's our first projector on the left qubit, tensor product. I wanted to avoid pulling up the screen again, but this is even more painful. Okay, I think I almost got it, but my eyes look like pluses, so please excuse me. Okay, this is minus I and minus I. Okay. And of course, you have to first understand how to construct this, but we've gone through an example with 0, 0. Hopefully, you can now construct for yourself what the outer product of plus and plus is, like plus with the bra itself. So you write down plus in column vector and take outer product with its bra, and that'll give you the appropriate matrix for this operator, and then you take the tensor product using the rules we've already looked at. And now, of course, with code, with Python or something, it's just a matter of programming in these two individual matrices and then taking Kronecker product. You get the answer. Okay. Any questions on this? This is not in your textbook, but I wanted to introduce it because I think it's important, because we have sort of talked about how you can project onto 0 and 1 in the multi-qubit basis. But when we did the single qubit, we talked about projecting into any basis. And it's not always clear to people, how do I go about making a linear algebra representation for projecting into any basis I want? Okay. And we can do that here. So one of the things that you may wonder is, okay, so I've done this in Python. You can, yes, you have a question? I thought you were raising your hand, sorry. You can do it in Python, as I've just shown you, or Mathematica. You just program it in differently with slightly different sound naming functions. But how do I implement this as, say, something that we can simulate on a quantum circuit or a quantum computer using Quark? Okay, so for that, I'll just go through that on the. Let's get this. Stop the share. So, we can use Quark to simulate projection or any gate operation. Okay, So here's the circuit. You may remember we produced code previously. So now, if I want to, like, for example, if I just wanted to do the Hadamard times the identity, we just did that, right? So remember, we did Hadamard on the left qubit, that's the bottom one, and identity on the right qubit, right? That was the gate that we did earlier. So if you look now, it tells you that after acting with this on the 0, 0 state, this is what will happen. And now I can go through all the ones that I just did, okay? So, and if you mouse over here, if you just sit on this block sphere over here, you can tell, okay, that is in the equator along the x-axis. And it also tells you over here for the entire state what the output will be, because it starts with 0, 0 on the top left corner, 0, 1 over here, 1, 0 over here, and 1, 1 over here. Okay. So it's telling us that there is, this is the state, okay, for amplitude of 0, 0, as you can see over here. Okay. The amplitude of 0, 0 is 1 over root 2. And that means, and the half-filled nature of this means there's a 50% chance of observing it in this state. And then over here, amplitude of 0, 1 is 0. Okay. Amplitude of 1, 0 over here is again 1 over root 2, and it has and that half-filled sort of shading indicates the probability 50% to observe that state. Okay. And of course, the other one is 0. Everybody following this? Any general gate that you want could be constructed, and then all we would have to do is put it into the one of the circuits. For example, I constructed a gate over here, which is similar to our quantum bomb detector gate. Okay, basically, what it does is you remember the quantum bomb detector, I rotated the 0, 1 basis slightly into the U and V axis. Okay, and that's basically this gate, okay, over here. But I have to use R dagger. If you remember, when I construct the gate, if I want to make a measurement in that basis, then I take the qubit and I feed it into the R dagger of that gate. Okay. If you don't remember this, we can go back over it, but I just wanted to quickly mention that this is the same gate as we constructed in that lecture on the quantum bomb detector, but I've made it into the dagger of that gate because I want to use it as a measurement gate. So I can take this gate and I can put it over here, for example. Okay. Maybe first to start with, I'll just show you what happens if I don't have the Hadamard. Okay. So you can say it doesn't look like there's much of a change, right? I mean, the gate has remained in the same state. It's off, meaning there's a very small probability of being on, obviously, because it's a 0 state in the input here. Okay. But if you can see what happens if I don't have the gate, then the probability is 0. This was a very small rotation. It was a 10-degree rotation. Okay, so the 10-degree rotation means it has only a very small probability that it will be observed in the one state, but it's not completely safe. It's not as small as it was before. So before it was 0% chance of being on, but now it's 0.00093% chance of being on. Okay, because it has a small rotation away from the block sheet, from the z-axis. For example, if I put 1, same thing. If I now change this input to 1, so instead of being 0, if I change it to 1, now it is almost 100% likely to be observed along the south pole. Okay, and when I mouse over there, it tells me that the block sphere representation and what this qubit is. And again, you can see, here, for example, the amplitude of the 0, 1 state is 1 plus 0 with a magnitude of 99.9991, but it's not quite 100%. Again, if you don't trust what this gate is doing, you can take it out. And now you can look and you see the amplitude is exactly, again, this plus a magnitude of exactly 100%. Okay. And if you look here, the probability is 100% of being on if measured. Okay. So the gate I was using there is that UV axis gate in the quantum bomb detector. So that's why it only slightly rotates the matrix. So if you want to make some gate that rotates by a little bit more, so for example here, this is the gate, I made the matrix, okay, and it has, you know, some operation. Let's say instead of 10 degrees, let's say I make it 30 degrees, you know, it makes it a little bit bigger. Yeah. Now, ensure unitarity. I'll give this a new name. So now I have a second gate over here. And now if I, instead of this gate, I put this gate over here, or that 2. Now you can see I have a much bigger chance of being on. Now it's almost 50%. Okay? Over here. Because it was a nearly 60-degree rotation, because remember there's an epsilon over 2. So when I did 30, that means it's actually, the actual rotation is almost 60 degrees in the plot sheet. Okay. So, yeah, so this is a much bigger rotation, almost close to, you know, 50% of the rotation. Okay, and, oh, sorry. My mistake. 0, okay, sorry, it wasn't so bad. Okay, so the probability has gone up a little bit more. It's now 0.0835% instead of being 0.0001 or whatever percentage it must be. All right, so okay, so that is how we make our own gates, and we can even make the gate that I was telling you about. So, for example, I can make a gate which is not unitary, and I can tell it, you know, this is the gate 1 0 0 0. Remember, this is the projector gate onto the 0 state. Remember, it is 1 0 0 0. Back here. If you look behind here, that was the gate. Okay, so I call that. And you know, it's warning you, this is not a unitary gate. Okay. Yeah, no problem. Okay. I drag this onto here. Okay. And you can see the projector of 0 onto 0. Well, yeah, I mean, you know, it has 0 probability to be observed in the on state. It's always in the off state. Okay. Okay. But if I now put 1, now you can see what it does. Okay. Because it basically destroys that 1, you know, you can think of it as cutting the wire or something. Whatever 1 was before, now it's being projected onto 0, but it has 0 probability to be observed in the 0 state. So this is a unitary gate. So you can see it even tells you it omits 100% of the state. It just kills it, basically. Okay. So this is the chance of being on, if measured, is this gate. Okay. We're going to turn it back to plus. Now, if it's plus, then it has 0.5%. Half the probability is omitted, which is whatever was in the 1 part is omitted, but the 0 part is kept. So it has 50% chance of being, you know, in the 0 state. And so it says it omits 50% of the rest of the probability. Okay. All right. So there's just an example of how you can actually make the gates yourself in Quark and simulate it. So I'll stop the share. Any questions on this so far? Oh yeah. So if we try to do this now, and as I said, we have projected the left qubit. Oh, sorry, this is the right qubit. We have projected the left qubit here. Remember, left is the bottom row of this circuit, right is the top row of the circuit. And so in this case, I've done nothing to the first one, and the second one has been projected into the 0 state. And now I can, you know, do other things, like I can operate with the projection with some other gate like this, and I can start to build up any number of sort of projector operators and things like that. So when I want to measure along the UV basis, I operate with R dagger, and then I project along the 0 state. Okay, because that's what it does. Because now when I rotate, basically I've made U and V as my new 0 and 1. Okay. So by operating with R dagger, I've essentially made the state project onto the UV basis, and then I measure it along the zero state to give me the answer. But of course, in our case, it'll already tell you what is the probability to be in the 0 or 1 state over here. It already tells you that. It tells you that this probability now is 50% to be observed after going through the R dagger. That's because it's not quite 50%. So if I didn't put the R dagger, it's exactly 50%. When I bring the R dagger in, or R dagger 2, whatever it was, I forget now. When I bring R dagger in, it now becomes 50.3% to be along that point in the equation, and so on and so forth. Okay, so this is just how we can make any kind of circuit simulation in Quark. Let me now go back to the slides. So I've illustrated both these cases in that what I just did on Quark. Okay, here's another example I'm going to do now. So we want to operate now with H on the left qubit and X on the right qubit. Okay, so let's go through these cases. I know it's a bit slow to go through all these cases by hand, but I figured I'll do it now, and hopefully after this, we won't have to do it by hand again and again. You'll begin to get the idea of it. Oh, well, first I should ask you. So do you see how to make a gate that does H on the left qubit and X on the right qubit? What should I write down in the Ket algebra notation? Or operator notation, whatever you want to call it. So H on the left qubit, X on the right qubit. Yes.
Would it be the outer product of H times the tensor flow, the outer product of X?
Wow, that's a lot of words. Outer product of H with tensor flow?
No, tensor flow,
Tensor product. So outer product, remember outer product is always taken between something like, a ket and a bra. Here, I'm asking, you're getting your flows, but so you're saying H, right?
Yeah.
And then what?
That's the tensor product,
With?
the outer product of X. This X, right? Where it's plus.
So I think there's a little bit of notation or naming confusion here.
Yeah.
Outer product is purely meant for when I'm trying to construct a matrix, when I'm trying to say construct like a projection matrix or something like that. Okay, so for example, if I want to construct the matrix that projects me onto the plus plus state, I do this. That is an outer product. Okay.
Yeah.
And the matrix that would project me onto say plus plus and minus minus, this will turn out to be an identity because plus and minus are complete set of states, okay, orthogonal states. H, for example, could be written as the plus plus with minus minus. So it'll give you, something like that, for example. Okay. So these are outer products, indeed. Okay. I think that's right. I have to. Yeah, I should be careful. Maybe I made a mistake. But the point is, that's the outer products. But I now want, so I think maybe the thing to remember is when we do 2 qubits, we use a different operator, which is the tensor product or Kronecker product in linear algebra notation. So for maybe this is a simple way to remember. When I want to create gates or operators in the 1 qubit space, I can use outer products. When I want to create gates in the 2 qubit space, I have to use, what is it I have to use? Tensor product. Very good. Okay. So you're right, it's a tensor product, but now I'm doing the gate that I'm writing is H, and now I want X on the 2nd qubit. So I do a tensor product with X. Is that clear to everyone? We're doing 2 qubit gates that we are constructing from single qubits. Then we do qubit 1, tensor, qubit 2. The gate on qubit 1, tensor with gate on qubit. In the last few minutes, let me just identify what this will do. So how do I go about constructing the matrix representation for H tensor with X? What should I do? H tensor X, how do I find its matrix representation? Any thoughts?
Yeah, you could either just compute it with matrices, or you could pass it through all 4 states and then one.
Exactly. Very good. Excellent. So there are 2 ways we have learned how to create a matrix representation. Method 1 is to simply operate on 0, 0, 0, 1, 1, 0, and 1, 1. And since each of these is a column vector, whatever output column vector we get here is our, and we stack all the column vectors side by side, and we get the matrix representation. The other way, as he said, is I can simply write down H equals 1 over root 2, 1, 1, 1 minus 1, and X, which is just the NOT gate, basically. So it's 0, 1, 1, 0. This is the NOT gate in linear algebra form, right? And then I can simply compute the tensor product of these 2 matrices. Okay, so this method is obviously going to be fairly quick. Okay, we just do it right here. So I'll just write it down 0, 1, 1, 0. So that's just multiplying this matrix times 1. Okay, and then over here is also the same matrix. So 0, 1, 1, 0, because it's 1, and then also 0, 1, 1, 0. And then the last one is 0, minus 1, minus 1, 0. Okay. So you can see it's very quick to get this, but for completeness, we want to also do this situation. Okay. So to do that, I'll have to take H acting on the left qubit, X acting on the right qubit. So that gives me 1 over root 2 times 0, and then X acting on 0 gives me 1. 1. Very good. Everybody see how we got this? And if you check over here, that means that the 0, 1 component will have a 1 over root 2 here. Sorry, that's 1 over root 2. That's over here. And the 1, 1 component will have a 1, because that's also in this superposition over here. So that's the first column of our H times X gate. Okay, I'll stop there for today. And in the next class, we'll finish up the finding this, the last 3 comments. Or maybe I assign it to you. Why don't you do that? Go back and make sure that all the other row columns follow like this example. If you have any questions about it or you're having trouble with that, just ask me in the next class.
I do have this next class. Where do I get a